All right, so topic 5.5, electric circuits. Electric circuits. So here we go. When we start talking about electric circuits, think about what we've done. We built this idea that there's a charge, and you have this charge, and around that charge exists a field, and around it, and also you can have a potential around that charge, and the fields will exert forces on each other. So now we're ready to start talking about these electrons as they're going to migrate or drift through the wire, the conductor. So the first thing that they want you to talk about is you open up 5.5 and read about is the EMF, electromotive force. You can look that up, electromotive force. This is sort of an interesting thing, EMF. I'm not really sure. I guess I understand why they want you to learn it, but the EMF is measured in volts, and for most purposes on a circuit, you don't really care about the EMF. But here's the deal: if you have a battery, and you were to, this is the plus side and the negative side, and I've given you some insight in what a volt, measuring the potential difference across something would look like. So if you had a battery and you measured the potential difference across the battery, and it was a 3-volt battery, let's say, and sure enough, you would measure basically 3 volts on this battery. But if you were to try to put this in a circuit, so let's just say that you hooked up a wire. Now remember that this is a voltmeter, very high resistance, does not allow current to flow through it or anything. It affects the overall circuit. But then you put a little light bulb right here, and that's a pretty junky looking light bulb, but it'll work. And it goes back to here, and then there's a little glass case around the glass encasement of the filament. There's our tungsten filament, W. And so anyway, if you were to now measure the potential difference across this battery, it would be just slightly less because of the internal resistance that resides in the battery. So the big thing about the EMF is that it's basically the potential when the battery's producing no current, so there's no conventional current flowing this way. Current the battery's producing is under no load, I should say. Then the EMF, which we'll abbreviate as, put our symbol right here as E, then the EMF equals V when it's under no load. But when you put it under load, it's a little different. And the reason it's a little different is because there's internal resistance in the battery. And so then you consequently get this new equation that the voltage that you'd get is equal to the EMF minus the current going through it. And just go back to that slide and think about that. The current's going right through the battery, around here, and there's some internal resistance from the chemical reactions in here, all little chemicals producing electrons in there, and that causes a slight difference in the voltage that you would get in the circuit. In this circuit, if you just measured the battery under no load, so E minus I, and then what they use for internal resistance of the battery is little r, whereas if you're talking about a circuit such as let's just do that battery symbol that I taught you, and use this, and let's just use this square to make a simple circuit, and this is R, has some resistance value R. Well, right here, across here, you would find that through the source right here, you'd find that you'd have a resistance or a voltage under load equal to I'm sorry, I didn't say that very well. Let me get rid of that. Oftentimes you'll see just a small little resistor along here, and they'll say that this is IR, and that's attributed to the internal resistance of the battery. So again, if you measure the potential difference on the battery under no load, you would get a V would equal E. But if you measured under load, you'd get V would equal E minus IR, so you'd lose a little bit. So basically, EMF is the basically how would they say that? The ratio of work done by the non-electrical forces W. Here, I'm going to read this from the book here for you. To a quantity of charge Q that moves from one terminal of the battery to the other. So, so EMF is equal to work over Q. So the ratio of the work done to move that charge from here all the way around back to here. So that's what they're talking about is the EMF, and so that's just a simple understanding of it, and that's really basically all you need to know. I think you might want to check the book out. There might be a couple other simple definitions, but that's really the biggest part that they want you to know. All right, so then we get to simple electric circuits. So let's see, how am I at? 6 minutes. I'm not going to go over 10 minutes. So simple electric circuits. So the first thing let's just draw a nice series circuit here. Let's make that a little longer to emphasize the positive. So we have a series circuit, meaning that they're all in a row. You have to go through one to get the other, just like you have to go through one baseball game to get to the other in the World Series. So all of them go in a row like this, and let's just have this a value of R, and R. It doesn't matter. It could be any number, but all these rules would apply. So in a series circuit, think about it. There's only one path. So one path leads to everything having the same current. So if this has a voltage V, so one path would lead only one way for the current to go through it, and so therefore current throughout this entire circuit is a constant. So current is a constant. Okay, and let's see if I can do this magic. Doesn't look like I can. There we go. I almost got it all. No, I don't want to do that. I'm just going to redraw it. Okay, so next up, 3 resistors running to here. We knew that current, and I'm just going to erase that. We have, so basically the I through the battery, you could say, or through the source, is equal to through R1, R2, and R3 is equal to the current through R1, which is equal to the current through R2, which is equal to the current through R3, and you could go on and on for that. Okay, now let's talk about the voltage. So remember, this is the voltage of some voltage V. So the voltage of the source is equal to the change in voltage across R1 plus the change in voltage across R2 plus the change in voltage across R3, and so on. If you added more resistors or loads, remember I tried to define what a load is, then you would find out that you would just sum up all the voltages. So what I'm saying is that if V happened to equal 20, then we would know that R1 plus R2 plus R3 would equal 20 volts. And they may not all be 1/3 of 20, but they would be, the potential drop across each one would be dependent upon the resistance in each one. But still, they would add up to 20. Okay, last little rule, and that is the resistance. And the resistance total is quite easy. I got 40 seconds to do it. So all we have to do to get resistance in a series circuit is equal to the sum of resistors. So therefore, in the previous case, it would be R1 plus R2 plus R3. And so there you have it. That's the basics of a series circuit. And we talked about what the current would be like, what the voltage would be like, and what the resistance would be like in all three cases. So I'm at 9 minutes and 55 seconds, and I'm stopping. So See you tomorrow. Bye.